In this video, I will be talking about transformations to polar coordinates and why you turn, or any transformation actually, not just polar coordinates, and why in specifically just polar coordinates, this is the example, you have an R at the front. And this number right here, this R, whenever you have the area element of your integral, is something that I guess adjusts for your transformation. So when you are turning x into r cosine theta and y into r sine theta in polar coordinates, there needs to be a number, like r in this case, that accounts for your change in variables whenever you're integrating. And that's called the Jacobian. So this r value is called the Jacobian. And another example will be spherical coordinates, where rho squared, or p, sine of phi is equal to, like dv is equal to this. And this is the Jacobian in this case, d dp, d phi, d theta, right? So the Jacobian is something that just takes your transformation into account. And I'll teach you how to actually solve for that, because the only polar coordinates and spherical coordinates aren't the only transformations. For this one, I'm just going to show you how to do a 2x2 matrix. So a two variable Jacobian. What I mean by that is polar coordinates is two variables, just r and theta. But spherical coordinates has rho, phi, and theta as well. And I'll teach you this in another video. So, how do you set up a Jacobian? Well, x is equal to r cosine theta, and y is equal to r sine theta. Now, let's go ahead and do this. We have to set up our Jacobian, or set up our Jacobian matrix. All right? And then the matrix is set up specifically like this. D, delta, x, delta, r. So your two variables are r and theta, right? And you have delta x, delta theta. Delta r, delta y, and delta theta. Now, I misspoke a little bit there. I said that the Jacobian matrix is specifically set up like this, but it's actually slightly wrong. And the reason being is that you can actually change the order of this, and you can still solve for the Jacobian properly, or the r value in dr d theta. The way that you want to set up Jacobian matrix, which is this, is specifically assigning certain rows, so across, with a variable, your original variables x or y, and assigning columns to your new variables, r and theta. So you can actually set it like this. You can actually switch your rows for x and y. So you can write delta y, delta, I'll leave that alone for now, and delta y, delta some other variable, delta x, delta, delta x, delta. But what you can do is also switch the columns of your new variables. So you can actually put theta here into this Jacobian matrix as well. But as long as your rows are specifically designated to one of your original variables, and as long as your columns are designated to one of your new variables, your Jacobian matrix is fine. Now, what do you do after you have your Jacobian matrix? Just solve for the determinant. Sort of like cross product, but you're going to be adding everything together. So, what do you do? Well, first thing I do is look at a diagonal for this. So in a 2x2 Jacobian matrix, you want to solve for the cross product like this. You look at the top left, and you multiply these values with each other. Delta x, r, times delta y, delta theta. So I multiplied these two values together. Then what you want to do is subtract the other cross multiple or side of determinant of your Jacobian. So after multiplying the top left with the bottom right, you multiply the top right with the bottom left, and then you get delta x delta theta times delta y delta r. So this is the general formula for your Jacobian in two variables. But let's solve this specifically for our polar coordinates. So what do these delta symbols even mean? Well, these stencil symbols are partial derivatives. So we are finding the partial derivative of our x function here with respect to r. So how do you do that? Well, for our x function up here, so we're just paying attention to this, you find the r partial, meaning we treat any theta value as a constant. Therefore, our partial derivative is cosine of theta. And again, for our x function, we find the theta partial, which means that our r functions are treated as a constant. But since this function is of a trig function, our partial derivative of this is this. And next, our partial derivative with respect to r of our y function, which is simply just sine of theta, and our y function with respect to theta is just r cosine theta. Our y function with respect to theta. I should put an arrow here, because technically these aren't equal. But then after that, what do you do? Well, it's simple. Just look at this general formula, or just remember that you multiply the crosses with each other. So you multiply first the top left with the bottom right. This is r cosine squared theta minus r negative r sine theta times sine, which is negative r sine squared theta, which is simply r cosine squared theta plus r sine squared theta. And if you simplify this further, let's actually move this up. If you simplify this further, you should get your Jacobian r. And I'll actually show you that work real quick. You factor in r, you get cosine squared theta plus sine squared theta, which is just r times 1, which is equal to r. And this right here is your Jacobian, and whatever you get whenever you solve your Jacobian, it's just multiplied by your area or line elements, or whatever these are. These are called differentials, I think. But yeah. So if you have any questions, put it down in the comment section. I'll be doing one for spherical coordinates as well, and I'll also be doing one where the transformations are more general.